Okay, let's dive in. You've brought us something really fascinating today. It connects something, well, quite practical, like an auction,
Yeah, like a marketplace mechanism.
directly to the really complex world of blockchain consensus. It feels like bridging two quite different domains.
It absolutely does. And what's really, I think, insightful about the research you've shared is how it proposes using the actual work of the auction itself.
The work, you mean the calculation.
Yeah, the heavy lifting of figuring out who gets what, who pays whom, using that as the engine for building and securing the blockchain record itself.
Right. Okay, so the source material for this deep dive
Yeah.
is this research paper, Double Auction Meets Blockchain, Consensus from Scored Bid Assignment.
That's the one.
And our mission here is to, well, unpack it,
Mm-hmm.
go beyond the title, really get inside this paper, understand the specific problem it's tackling. It's pretty innovative solution,
Definitely innovative.
and most importantly, pull out why this whole idea matters, drawing directly from the material you've shared with us.
And it's worth mentioning, this is a really collaborative effort. It comes from joint work between researchers at places like the Institute of Science Tokyo,
Okay.
working alongside folks from Input Output Global, IOG,
Ah, yeah.
Mitsubishi Electric Corporation, the University of Kitakyushu, and also Hokkaido University. So a real mix of academic and industry minds looking at this.
Interesting mix. So let's start with the problem they're focused on, these double auction systems.
Yeah.
We kind of have a general idea of auctions, but what exactly is a double auction, and what's the core challenge the paper highlights there?
Okay, so think of like a stock market or any market where you have buyers submitting bids what they're willing to pay and sellers submitting asks what they want to sell for.
Simultaneously.
Simultaneously, yeah. A double auction system is the mechanism that takes all those bids and asks and matches them up to facilitate trades. It's definitely more complex than just one buyer, one seller.
Because you've got lots of people on both sides.
Exactly. And the system has to figure out, the best way to clear the market to match those bids and asks efficiently and fairly.
Okay. And the paper points to a critical need within that complex clearing process,
Hmm.
something missing or needing improvement.
Precisely. Once all the matching is done, the trades are assigned, who bought what, from whom, at what price. You absolutely need a transparent way to record those results.
Transparent so everyone can see it happen fairly.
Right. And crucially, immutable. It
Hmm.
needs to be set in stone, basically. You need a record that everyone can trust and know for sure hasn't been tampered with after the fact. It's fundamental for the market's integrity.
Which, okay, that immediately makes you think blockchain, right?
Yeah.
That's kind of its whole promise, providing that robust, tamper-proof ledger. The paper even mentions Bitcoin as an example of systems built for persistence and liveness.
It does. Those properties, persistence, meaning the record stays put, and liveness, meaning the system keeps running, are exactly what you need for a reliable auction record. Now, usually, if you wanted to use blockchain for an auction, you might say, build a smart contract that runs on top of an existing blockchain like Ethereum.
Right, or maybe use a layer 2 solution.
Or layer 2, yeah. Those methods basically record the outcome of the auction onto the chain. The chain acts as the notary, you could say.
Okay, right. But this paper, this is where it gets really interesting and honestly quite clever, isn't it? They did a fundamentally different path.
That's a core innovation, yeah. It's really neat. Instead of just using a blockchain as a separate recording layer for the auction results,
Uh-huh.
they propose constructing a provably secure blockchain protocol directly from the computation of the bid allocations themselves.
Wow. Okay, hold on. So the auction's mechanics, the actual calculation,
Yeah.
that becomes the blockchain's mechanics.
Essentially, yes. The process of solving the auction is intertwined with the process of building the blockchain.
So building the consensus mechanism out of the auction's own complexity, that sounds like it needs a completely different way to think about proof of work. What's the central technical piece they designed for this?
Well, they designed exactly that, an alternative proof of work or POW scheme. In standard blockchains like Bitcoin, POW often involves solving these sort of arbitrary crypto puzzles.
Right, like SHA-256 hashing. It's just a hard computation.
It's hard computation, and that work is what secures the chain, prevents spam, helps select the leader who gets to propose the next block.
Okay. It's the cost, the effort you put in to earn the right to add to the ledger, making it expensive for bad actors.
Okay.
So their alternative of POW, what kind of work is it based on?
It's based on solving or at least scoring solutions for what they call a scored generalized multiple assignment problem, SGMB for short.
It is GNA.
Cool.
Okay. Scored generalized multiple assignment problem. That sounds related to the auction itself.
very related. The computation involved in finding good solutions, or even just evaluating how good a potential solution is for this specific type of assignment problem that becomes the work in their proof of work system.
So hang on. Instead of miners solving some random puzzle completely unrelated to the auction,
Exactly.
the work is directly tied to the core computational task of the auction itself, figuring out the assignments.
That's the idea. How does that drive leader selection then in their specific blockchain design?
Well, leader selection deciding who gets to add the next block containing the latest auction results, it's driven by block scores.
Block scores, derived from the SGM.
Derived directly from their SGM scoring function, yes. The better the solution or score you find for the SGM within certain difficulty parameters set by the system, the higher your block score. And a higher block score means a better chance of being selected as the leader for the next block.
And the abstract mentioned something about the SGM scoring function being flexible. That sounds important. It's crucial. Yes, it's designed so it can be tuned. You can define the difficulty level of this, well, proof of assignment work, if you like.
Proof of assignment, I like that.
Yeah. And it can also accommodate the specific real-life requirements of whatever double auction system it's being used for. So it links the difficulty of creating a valid block directly to the complexity of solving or scoring the bid assignment problem for that particular market.
So the effort to secure the record is literally the effort to process the market results. That's elegant.
It is rather elegant, isn't it?
Okay, so they've designed this really clever mechanism, tying auction computation directly to blockchain work. Did they actually prove that it works, that it's secure?
Well, according to the research, yes. They provide theoretical guarantees for their design. Specifically, they proved persistence and a modified liveness property.
Okay, so for you, the listener, persistence basically means that once those auction results are recorded in a block on this special chain, that record is reliable. It's incredibly difficult to alter or reverse it. It sticks.
Exactly. And liveness, well, it means the system keeps going. New blocks containing new auction results can continuously be added to the chain. So the market doesn't just grind to a halt. It keeps running.
Yes.
And its results keep getting recorded over time.
So they established that their SGMP-based design achieves these fundamental blockchain properties, secure and functional.
That's what the theoretical proofs show, yes.
And theory is one thing, but did they look at whether it's actually practical? Can you build this?
They did. They present implementation results in the paper as well. They wanted to validate its robustness and its practicality. So, yeah, they didn't just stop at the theory. They actually built and tested it to see if it holds up in practice.
That's good to hear. It wasn't just a thought experiment.
Right.
And bringing it back, just for context, we mentioned the collaboration earlier. It really was a significant multi-institutional effort behind this.
Absolutely. As we said, Institute of Science, Tokyo, IOG, Mitsubishi Electric, University of Kitakyushu, Hokkaido University. That kind of diverse expertise tackling this specific problem is pretty significant, I think.
Yeah, it suggests the problem has broad relevance. And this research, it's not just sitting in a lab archive, is it? It's been accepted for presentation.
That's right. The paper has been accepted for presentation at ACNS 2025.
ACNS.
The 23rd International Conference on Applied Cryptography and Network Security. It's happening this June, and the paper will be presented there. So it's getting out into the wider research community.
Okay. And looking at the paper's own history, the metadata suggests it's been, well, cooking for a while.
It has. It looks like it was first received way back in October 2022.
Wow.
And it's gone through revisions since then, with the latest one noted in January 2025. So yeah, it's definitely been through a process of refinement and review.
That adds some weight to it. And for you, the listener, if you're intrigued by this and want to, read the source yourself, where can people find it?
It's publicly available, which is great. You can find it in the Cryptology ePrint archive.
Yeah.
If you search for paper number 2022-1471, that's the one.
2022-1471.
Got it. And it should also be available on the IOG library website.
Excellent. So accessible for those who want to go deeper.
Yep.
Okay. So let's try and tie all this together then.
Yeah.
Why is this idea, building a blockchain directly from the computation of the auction itself, why is that significant? What are the big takeaways here for you, the listener?
Well, I think it inherently links the trust you need in the auction's outcome directly to the security mechanism that records that outcome. Does that make sense?
Yeah, I think so. The very complexity, the computational difficulty of fairly allocating all those bids and asks.
That is the effort. That's the work that validates and secures the block containing those results.
So it could potentially offer maybe a deeper level of transparency or built-in trust for systems that rely on these complex matching or allocation processes, not just auctions, perhaps.
Potentially, yes. And I think it also highlights a really fascinating direction in blockchain research overall. Instead of always thinking about blockchain as this separate general-purpose security layer that you apply to an application, they're exploring how the specific requirements and the core computations of the application itself, like this bid assignment problem in double auctions, how that can be the source of the consensus mechanism.
Tailoring the trust protocol to the application's own intrinsic complexity.
Exactly. It's a very integrated approach.
Okay, so just to quickly recap for everyone, this research, coming from collaborators across multiple institutions in Japan and IOG, explores a really novel way to merge double auctions and blockchain. They do this by building the consensus mechanism, the blockchain's core security, directly from the bid assignment problem inherent in the auction.
Using that alternative proof of work based on the scored generalized multiple assignment problem, the SGMA.
Right. And they've proved its theoretical security, persistence, and liveness, and also shown its practical robustness through implementation.
It's a really elegant concept, isn't it? Using the problem you need to record as the very source of the work needed to secure that recording system.
It really is. Which leads us, and you, the listener, with a thought to maybe carry with you. If the intricate mechanics of clearing a complex auction, if that computation can actually be the engine that secures its own transaction record on a blockchain, what other complex processes out there, maybe other market designs or even fundamental scientific computations or logistical problems, could they potentially be the source of their own built-in transparent consensus mechanism?
Making the proof of the work literally the proof of the record's integrity.
Exactly. A fascinating direction for future work, perhaps.